These were two great talks. This is a really hard pair of acts to follow. I'm not going to talk about nutritional immunology, so it's going to be an easier 20 or 25 minutes. I'm going to talk about omega-3 fatty acids, which are really the nutrients that most of our research has been done on. The omega-3 and human health story is a very old story, dating back to the 1970s. Of course, there are always nice new findings in the research area. I'm going to present data from two of our studies today. Some of that data isn't yet published, but I think will be accepted for publication very soon. So there are always new things coming along, but the story has a very robust, solid, long-lasting base, which hasn't changed despite many things that people might say. So some people are looking a bit quizzical. This is the new UK £1 coin on the left. So when I'm talking about omega-3 fatty acids, I'm talking about eicosapentaenoic acid and docosahexaenoic acid. These are very long chain, highly unsaturated omega-3 fatty acids. So this is a sort of a cartoon depiction of a fatty acid structure. EPA has 20 carbons, DHA has 22 carbons, EPA has 5 double bonds, DHA has 6. The terminal double bond is on carbon number 3, which makes these omega-3 fatty acids. The main dietary source, or rich dietary source, of EPA and DHA is seafood, particularly oily or fatty fish, whatever you want to call it, things like salmon, sardines, herring, tuna, and so on, mackerel. But those omega-3 fatty acids are also available in supplemental form, and those supplements, of course, will provide different concentrations of EPA and DHA depending upon the nature of the processing. But the presence of omega-3 fatty acids in supplements, including in concentrated forms, makes it quite easy to do randomized controlled trials with these nutrients. What we know is that omega-3 fatty acids have a very important role in protecting against the development of cardiovascular disease. This is a study from the Nurses' Health, data from the Nurses' Health study, a big epidemiological study in the US. And what the researchers did here was they quantified EPA and DHA intake from the diet of these nurses when they were middle-aged and disease-free, and then they tracked those nurses over a period of time, and the outcomes here are the development of coronary heart disease, dying from coronary heart disease, or having a myocardial infarction, that is a heart attack, which isn't fatal. And they set those outcomes according to quintile of EPA and DHA intake when the women were disease-free, with the assumption that that sort of intake would be maintained lifelong. So they set the risk of these outcomes at 1 for the women with the lowest intake of EPA and DHA, and as you see, the higher the intake from the diet, the lower the risk of these cardiovascular outcomes, with a risk reduction of something like about 50% in each of the outcomes. And an individual would find themselves in this highest quintile of intake either by eating more seafood, particularly oily fish, or by taking omega-3 supplements. This is similar data from another very well-known epidemiological study from the US, the Physicians' Health Study. In this particular paper, the amounts of EPA and DHA were measured in blood of these physicians when they were middle-aged and disease-free. And the outcome here is sudden death, so this is a mortality outcome as a result of a myocardial infarction, according to the quartile of EPA and DHA status in the blood when those physicians entered the study. So again, the outcome was set at a risk of 1 for those with the lowest status of EPA and DHA in the blood. And you see as the status increased, so the risk was reduced by as much as 80%, even after adjusting for many, many other cardiovascular risk factors. And again, just to emphasize, an individual would find themselves in this quartile of having a lot of EPA and DHA in the blood if they were eating a lot of oily fish or using omega-3 supplements. So those are two individual studies, one looking at dietary intake and one looking at EPA and DHA status. In 2014, meta-analysis was published in Annals of Internal Medicine by Calder. This is actually a much maligned meta-analysis, and I'll tell you why that is in a second. So what these researchers did was they gathered together all of the epidemiological studies where researchers had reported dietary fatty acid intakes and had related those to coronary outcomes, that is things like developing heart disease, needing surgery for heart disease, or having a heart attack in the period beyond when the dietary data was consumed. So the types of fatty acids are here, and the reason this meta-analysis is much maligned is it shows there's no effect of difference in saturated fatty acid intake on coronary outcomes, which of course goes against all of the advice from every country in the world, I think. But what the study does show is that having a high dietary intake of what are called long-chain omega-3 fatty acids, that is EPA and DHA, is associated with a lower risk of coronary outcomes compared with having a low intake of those fatty acids. This is consolidating data from 16 studies involving 422,000 people. So I think this is, reasonably convincing evidence. The second element of this meta-analysis was the aggregation of studies where fatty acids had been measured in the bloodstream. This is the omega-3 fatty acids. Individually, EPA, DHA, an intermediate, this is EPA plus DHA together, and an intermediate in the biosynthetic pathway of EPA to DHA. This is docosapentaenoic acid, or DPA. And what the meta-analysis shows is those individuals with a higher amount of these fatty acids, either individually or together in the blood, is at a lower risk of developing coronary disease over the following period than people with a low status in the blood. And again, you see the numbers of studies and the numbers of participants. So this is very solid, recent evidence from meta-analysis of epidemiological studies showing that those people with a high dietary intake of these fatty acids, or with a higher amount of those fatty acids in the blood, have a lower risk of coronary disease over the follow-up period. How can that protective effect of omega-3 fatty acids come about? Well, we have to look at the risk factors for cardiovascular disease. These are listed here. And here I put ticks beside those risk factors where there's very good evidence that omega-3 fatty acids have a beneficial effect. So these fatty acids act to modify the risk factor profile, so making people less at risk of developing the condition. As a result of that sort of thinking, some researchers, Bill Harris and Clemens von Schacke, developed a concept called the omega-3 index. This is simply the amount of EPA and DHA as a proportion of all fatty acids in the red blood cell membrane. So what they wanted to do was develop a number, rather like a cholesterol number or a blood pressure number, where you could identify the risk of an individual for coronary heart disease according to omega-3 fatty acid status. So what they said was people who have less than 4% of EPA and DHA in their red cells are at high risk. People who have more than 8% are at low risk, so they have the greatest protection, and there's an area in between where people are at moderate risk, and I'll come back to that later on. The other thing, of course, that's very important in nutrition is that we understand the mechanisms of action of nutrients that explain the physiological effects and the influence on health and disease risk. So omega-3 fatty acids in general act by being incorporated into cell membranes, and once they're incorporated into cell membranes, they change the physical nature of the membrane, they change some functional aspects of the membrane that are very important in the way the membrane acts to generate signals that tell cells how to behave, and they act as substrates to produce various chemical mediators that influence the cells in the local environment. So these are different types of signals that cells are producing either intracellularly or extracellularly. So these influence cell and tissue responses, influencing physiology, so that's how all of those different risk factors that I showed you before are affected, and this results in improved health, decreased disease risk, and better clinical outcome. So the upshot of all of this is that having more omega-3s in the blood, in cells and in tissues, is associated with better health. particularly better cardiovascular health. Let's look now at how we might think about having more omega-3s in the blood. So we eat fatty acids usually as components of dietary triglycerides. This is true whether omega-3 fatty acids come from fish or from supplements. In the gut, they're digested and absorbed, and I have a little bit more detail about that later on. And as a result of the absorptive process, they appear in the bloodstream as components of big complexes called lipoproteins. Those lipoproteins are, if you like, buses for delivering fatty acids to different tissues. Those lipoproteins have proteins that are recognized by receptors on different tissues, and so they deliver the fatty acids to different places. These could be to the liver for metabolism, they could be to fat tissue for storage, or they could be to any cell or tissue in the body where those fatty acids are used to build cell membranes. So we can think of these different pools of fatty acids as transport pools, storage pools, functional pools, and metabolic pools. So we have many different compartments in our body. So every cell has a membrane. Every membrane has many different fatty acids. So we have many different compartments. We have different chemical forms in those compartments. Within one compartment, like blood, there are many different pools: red blood cells, white blood cells, platelets, triglycerides, phospholipids, and so on. And the content of EPA and DHA is different in every one of those pools. So there's a selectivity about where those fatty acids are going in terms of their cellular and tissue distribution. We have been interested for many years now in the relationship between increased intake of EPA and DHA and the amounts of those fatty acids that appear in different pools within the human body. So I want to illustrate some of what we've done by talking about this paper, which was published 12 years ago, funded by the UK Food Standards Agency, which of course is a government department. So what the Food Standards Agency were interested in was whether they could identify, through good science, biomarkers of oily fish intake. So they wanted to know more about the relationship between the intake of EPA and DHA and the appearance of EPA and DHA in different body compartments. So we were very fortunate to get this funding to do a dose-response study of supplements of omega-3 fatty acids, but delivered in a very novel study design. So this is a 5-group parallel design study where healthy individuals were randomized to those groups, stratified according to age and gender. One group was a control group. They didn't consume extra EPA and DHA beyond their habitual diet. These were low oily fish consumers. Then we had one group of individuals who consumed 2.8 grams of EPA and DHA on one day per week, and on the other 6 days they consumed placebo capsules. The second group consumed 2.8 grams of EPA and DHA twice per week, and on the other 5 days they consumed placebo capsules. There was another group, which I'm not going to mention again in the study, so I don't need to tell you about that. In the talk, I don't need to tell you about that. And then the 5th group consumed 2.8 grams of EPA and DHA 4 times per week, and on the other 3 days, they consumed placebo capsules. So this is a dose-finding study with an interesting design. 210 people, 105 in Cambridge and 105 in Southampton. So we recruited those 210 people. They were randomized to the 5 groups. They came into the clinical research facilities 9 times over 12 months. So this is a 12-month intervention. And we took blood on each occasion. We took mouth washes on each occasion. And we took adipose tissue biopsies 3 times during the study. And we conducted fatty acid composition and analyses on material from all of those clinical visits. We analyzed the fatty acid composition of 4 different blood lipids, of platelets, of red blood cells, white blood cells, of cheek cells, and adipose tissue. This is 18,000 samples that were analyzed from 210 people who paid 9 visits to a clinic for a 1-year intervention. This was an awful lot of work, but the data are very clear as shown here. So this is an example of the way we showed the data. This is 1 year intervention here. This is the amount of DHA in plasma phospholipids. In the control group, this didn't change over 1 year. And then remember, we had 3 doses which were equivalent to the amount of EPA and DHA which would be delivered in 1 oily fish meal per week, 2 per week, and 4 per week. So you see this is a very nice dose-response relationship. And you see in plasma phospholipids, DHA reached a new steady state at 60 days of intervention. That steady state was reached irrespective of dose, and they were maintained at that plateau thereafter. So we were able to, the details of the rest of the study don't really matter, but we were able to define the dose and time-dependent incorporation of EPA and DHA into 9 different body pools over 1 year. So we identified in great detail the time course and dose dependence of EPA and DHA over a long period of time. This is extremely important because I already mentioned that getting omega-3 fatty acids into cells and tissues is the key to unlocking the health benefits of those fatty acids. So understanding the way that the membranes are changing, or the cells and tissues are changing in response to increased supply, is very important. So we knew how much we were delivering orally, we knew how much was in the blood because we measured those different blood pools, and then we knew how much was in certain cells because we measured red cells, white cells, platelets, adipose tissue, and so on. So we uncovered some interesting relationships there. One of the things that industry has been very interested in is, are there ways to get even more omega-3 fatty acids into the blood other than simply just consuming more in the diet? Of course, one answer is just eat more fish, take more supplements if that's what you choose to do. But are there other ways to do that? So here we have to think about how fat is digested and absorbed. So of course the fat from our meal forms a lipid droplet emulsion. That is broken up into micelles as a result of the release of emulsifying agents like bile salts into the upper small intestine. So smaller micelles are produced. They enable the lipase enzymes to access the triglyceride and digest the triglyceride into a monoglyceride and free fatty acids. The monoglyceride and free fatty acids are taken up into the enterocyte. Triglycerides are reformed. These big complexes called chylomicrons are produced, and in the end they are released into the lymphatic circulation and then into the bloodstream. So emulsification is a very important part of fat digestion that ultimately enables the hydrolysis to occur and the absorption to occur. So industry have been spending a lot of time trying to find ways to enhance the absorption. They like to call it bioavailability, but many people argue that's not the appropriate term, to increase the absorption of bioactive omega-3 fatty acids. Now, and many different strategies have been used. Researchers have developed systems whereby lipid emulsions can be formed in situ, that is either in the stomach or in the upper small intestine, once the encapsulated, the capsule of an omega-3 supplement breaks. So this is called a self-emulsifying drug delivery system. Of course, the pharmaceutical industry is very interested in this sort of approach. So we have conducted a very fascinating study, which, as I said, we hope to have accepted for publication very soon. I'm supposed to be working on the revisions while I'm here, but instead of that, I'm coming here and giving you a talk. But so this is the first study that looks at the effect of these in situ emulsification strategies to deliver omega-3 fatty acids in human beings. So we use omega-3 ethyl esters because industry has developed highly concentrated ethyl ester preparations of EPA and DHA. This is a study in 80 healthy people who were divided into 4 groups. One of those groups consumed an ethyl ester preparation that contains both EPA and DHA but is very rich in EPA. A second group consumed an ethyl ester preparation that is very rich in DHA, although it contains some EPA. And then those were compared to the identical ethyl ester preparation that was presented in the self-emulsifying form. The total EPA and DHA is matched across all 4 of these groups at 1.3 grams per day, although of course these 2 groups are consuming more EPA and less DHA. These 2 groups are consuming more DHA and less EPA. So we did a single dose study where EPA and DHA were tracked in plasma for 24 hours after single dosing without a meal, which is very important. And then those people continued their daily dosing, and we tracked EPA and DHA in plasma, white cells and red cells for 12 weeks with repeated daily dosing at least 30 minutes before breakfast each day. This study was completely funded by industry, by a company called Pronova Biopharma, who were bought about 5 years ago now, I guess, by BASF. And the result of that actually is this old drug company name is going to disappear this year, and Pronova won't exist anymore. So this is plasma EPA and DHA after single dosing. So I'll just orientate you to the slide. So on the top here, this is the comparison between the normal ethyl ester form of EPA and the self-emulsifying form. This is the appearance of EPA in plasma and DHA in plasma, because remember there's some DHA in here. This is the comparison between the normal DHA ethyl ester and the self-emulsifying form of DHA ethyl ester. Again, this is the DHA, but there's some EPA in that formulation. So these unfortunate volunteers consumed this single dose, fasted, and without a meal, and they only had some light snacks over the following 24 hours. So the key things to see, if you don't have a meal, you don't get your omega-3 fatty acids appearing in the bloodstream. And that's because you need a meal to generate the release of the bile and the enzymes that play a role in the digestion and absorption. However, if you provide the self-emulsifying formulation, you don't need a meal to deliver EPA and DHA to the bloodstream, which is pretty amazing, I think. I didn't think this study would actually work. So these results are pretty incredible. So that's after a single dosing basically without any fat over 24 hours. This is actually even more fascinating. This is what happens if people actually resume their normal life, except they take the dose 30 minutes before breakfast every day for 12 weeks. So this is the sort of normal appearance of EPA and DHA that you would get into, this is total plasma, I think. And this is what happens if you use the self-emulsifying preparation. So even when people are consuming meals, this self-emulsifying preparation seems to deliver more EPA and DHA to the blood and to red blood cells. So here you see now the comparison of the ethyl esters of EPA and DHA with the self-emulsifying ethyl esters over 12 weeks, that you even get more EPA and DHA in the red blood cells. And I introduced to you before this concept of the omega-3 index, which is proposed as a cardiovascular risk factor. And here I have aligned the data we have for red blood cells for EPA and DHA added together for red blood cell omega-3 index in the ethyl ester groups and the self-emulsifying ethyl ester groups. And you see that in the self-emulsifying groups, many of the individuals are getting to above that threshold for good cardiovascular protection. In fact, if I remember the figures rightly, in the traditional ethyl ester groups, only 17% of people got above the threshold of 8%, whereas in the self-emulsifying groups, it was over 65% of people reached that threshold. So this is pretty satisfying, I think. So what I've told you is that omega-3 fatty acids, EPA and DHA, act on cells to alter cellular behavior in a way that optimizes cellular responsiveness. Epidemiological studies and randomized controlled trials show that higher intake of EPA and DHA is linked to improved health. I've concentrated on cardiovascular health, but this is true for many other areas as well, including early life development of mental and cognitive function. We know a lot about how blood and blood cells, and to a lesser extent tissues, respond to different amounts of omega-3s. Increasing delivery of oral omega-3s is attractive to industry and might be clinically relevant. So people get more omega-3s in their blood with the same size capsule, or they could take smaller capsules and get the, if you like, the normal amount appearing in the blood. So this is very attractive, I think. One human study, which is ours, shows higher enrichment of blood pools than a standard preparation, and I think omega-3s are really important to human health, and they also present really interesting commercial opportunities. Thanks very much for listening.